Okay, calculus, we're going to try this video again. We actually tried it earlier and it wasn't uploading, it wasn't even converting. So I'm going to do it one more time. Big idea here, we're doing derivative or differentiation techniques with differentiation. Again, here's all the things that we're using. Let's jump right into it. Okay, so the first thing to kind of be thinking about is what type of shapes you have. Like for example, if you have x squared, that looks kind of like this. If you have x, that looks like this. And if you have a constant, that looks like this. Or not even like that. Perfectly horizontal. Let's take this back a couple steps here. Perfectly horizontal, it would be like this. Okay, so the real question we're looking at is the slope of each of these lines. So when we're doing constants, which we're about to deal with here, you got to think about what's the slope of this line. And that's how we get our first rule, the constant rule. The slope or the derivative of this function equals 0. So as long as this is a number, not some type of variable, not necessarily a letter, but just some type of variable, then it's 0. The slope of a constant is 0. So 7, the slope of just 7, which is a horizontal line, is 0. F of x equals 0, that's still a horizontal line. And here we still have 0. So 0, 0, 0. This last one is a little bit interesting because this looks like a letter. This pi looks like a letter, but pi actually represents one number. Not just any number, not some type of variable, but one number. It's approximately about the 3.14. And a here is going to be treated like a constant as well. So what's the slope of a constant? It's 0. Oh, surprise, surprise. 0 across the board. So you got a constant, nothing else. Notice it's just a constant. There's no x next to it, below it, around it, to the power of. It's just a constant. Then the slope is 0. Let's take a look at the next one. Similarly, if we're taking the derivative of just x, it's going to equal 1. Because if you think about x, its slope is like this, where it's rise over run, I guess you could say, is 1 over 1. So what's the slope of this function? 1x is just 1. And what's the slope of this next function? It's again 1. And what's the slope of this function? Now this is in terms of t, but the slope is 1 over 1 here. It's a linear function, and the slope equals 1. Now notice again that this is x to the first power, or t to the first power, or some variable to the first power, meaning that it's linear. And linear functions have that constant slope, whatever that coefficient is. Similarly, which we're going to see in a second, if we had a constant out front, what's the slope of this? It's 2. Always. Why? Because it's linear function. Constant slope. Not a constant value, but the slope is always going to be the same. Okay, the classic power rule. This is like the one rule that everybody remembers, even when they forget all the other ones. The pattern is you got x to some power, or a variable, I should say, to some power. You're going to drop that power and then subtract 1. So right here, y prime is we're going to drop that 2 out front, and then it's x to the first power, because 2 minus 1 is 1. Similarly, this next one, we write it as f prime of x. We're going to drop this 6 out to the front and subtract 1 from 6. That gives us 5. This third one, again, pretty straightforward, pretty easy. S prime of t is going to be 30 times t. Now we subtract 1 from 30, we get 29. Okay, part D here, and for the rest of them, in fact, we have to do a little bit of prepping. We have to prep it so it looks like x to some power in a numerator. So this first one, anytime you have a square root or any root, it's really a denominator. It's like a fractional power. That means that this would become x to the 1/2. Now down here, this third root of t, that means that would have been 1/3, and we'll deal with that when we get to it. But x to the 1/2 is our power. So now when I take the derivative, I still follow the same kind of process. I'm going to drop that power. It's going to become 1/2 x. And now I got to subtract 1 from the power here. That means it's going to be negative 1/2. Now there's more algebra you can do. You can simplify that further, but you don't necessarily have to. If you did want to, this negative power means that it goes to a denominator. In other words, we'd have 1 over 2 x to the 1/2. And if I wanted to simplify it even more, I could make that 1/2 power back into a square root. It'd be 1 over 2 square root of x. On a multiple choice test, this is what you would see. For our purposes, you can stop once you got the actual calculation done, I guess you could say. All right, the next one. Okay, opposite of dropping it down to the denominator if it has negative power, if we bring it back up, we give it back the negative power. So this really equals x to the negative 1. That means that if y equals x to the negative 1, then y prime, we're going to drop that negative 1 out front, times x, and now we subtract 1 from the power. Now keep in mind, it doesn't just go 1 lower, because sometimes, well, it does, but some people think that 1 lower than negative 1 is 0. But it's not. X to the negative 1, when you subtract 1, that becomes negative 2. So this is going to be equal to negative 1 x to the negative 2. Now if I were to bring that power to the denominator, we'd have negative 1 over x squared. Alright, we keep getting a little more complex here. Now we're going to have f of x equals, now we got to bring this back up, same like we did in the last one, it'd be x to the negative 3. That means that f prime of x, we're going to drop that negative 3 out front. And we have x, and then we're going to subtract 1 from the power, giving us negative 4. If I were to do the algebra to simplify this again, we'd have negative 3 on top and x to the 4th on bottom. That negative drops it down. Okay, this next one, we got s of t equals, okay, we got a combination play here. We're going to do this in 2 stages. S of t is really 1 over t to the 1/3. But we know that we can bring this up to the numerator to make it look like our format that's easier by adding a negative to that power. So this is going to be t to the negative 1/3. That means that s prime of t is going to be negative 1/3. We drop the power out front times t. Now we got to subtract 1 from negative 1/3. That gives us negative 4/3. If I were to simplify more, this negative power brings it down to the bottom, so we'd have negative 1 over 3t to the 4/3. And this t to the 4/3, if I were to simplify that, it'd be negative 1 over 3 times the 3rd root of t to the 4th. Was that necessary? Not really. You don't have to simplify, but you can. Okay, this one, not so much a combo play. We just need to bring the power up to the top, so it's going to become x to the negative 3/4. So when we find y prime, or in this case, let's do dy dx, it's all the same. That's going to give us, we drop the power out front, negative 3 over 4 times x. Subtract 1 from negative 3/4, get negative 7/4. Let's drop that to the denominator. It's going to be negative 3 over 4 times x to the 7/4. And then rewrite this with a radical. It'd be negative 3 over 4 times the 4th root of x to the 7th. A lot of work there, but still pretty doable. All right, let's look at this next one. Now we're going to deal with power rule and moving things all around, but we're also going to have a constant here. And look at what happens to this constant. It's almost like nothing happens to it. It just sticks there. So when you have a constant combined c times x to the n, that c is going to stay there, that constant, but then we're going to have this nx to the n minus 1. We're going to take the derivative of the variable, but we're going to leave that constant just there. It's like a tag along, like that little sibling. Never goes away. So this first one, let's rewrite it. The constant in this case would be 2, but x by itself was going to be x to the negative 2. So now when we take the derivative, y prime, the constant stays there. But taking the derivative of x to the negative 2, that's going to give us negative 2 x to the negative 3. Now we can do some simplifying if we wanted to. 2 and negative 2 multiplied is going to be negative 4. X to the negative 3 is really over x cubed. All right, let's look at the next one. Please recognize again that we have a constant here, both a numerator and a denominator. So it's really 4/3 times x cubed. So when we do the derivative f prime of x, that's going to give us 4/3 out front. And then the x cubed is going to become 3x squared. Now I'm showing all my steps here. You can do some of this in your head, but it's good to write out your work so you can see what happened. Because right here I see that two things are going to simplify. The 3 in bottom and 3 on top is really 1 over 1. Now I have 4x squared. And that's my final answer there. Okay, this next one, the constant is really just the negative, which is really negative 1. So if I really wanted to get picky, I could write negative 1 and then t to the 5th. So s prime of t is going to become negative 1 times 5t to the 4th. Now simplifying that is actually pretty basic. We didn't necessarily need to write it like that. We get negative 5t to the 4th. Excellent, excellent, excellent. All right, let's look at this one. First, let's change this root, this radical, into a power. That means we're going to have 4 as our constant. Then x to a power is going to be x to the 1/2. And that means our derivative, dy dx, y primed, all the above, is equal to that constant. It stays there. Now we're going to do the power rule. That means we pull down the power, it's 1/2. Then x, we subtract 1 from 1/2, we get negative 1/2. So now we can simplify a little bit more. 4 and 1/2 really makes 2. And this x to the negative 1/2 means it's over square root of x. I did a combination there. I dropped it down to the bottom and said 1/2 is going to mean square root. Let's keep moving on because these are good examples. They show a lot of kind of breakdown of how this works out. This one, so our constant is negative 5 over 3. The power, though, is going to be x to the negative 3. Notice it was in the denominator, but I pull it up here to the numerator and I make it a negative power. That means that y prime, we're going to leave the constant alone, negative 5 over 3. Now I'll do the power rule with the other part. It's negative 3x. Then I got to subtract 1 from the power and I get negative 4. 3 and negative 3 simplify to just negative 5x to the negative 4. Now I can simplify that even more because that's really negative 5 over x to the 4th. Okay, let's look at this next one. I want to say that the constant is negative 5 over 3, but there's something that's kind of catching me. It's this cubed, because that's not really a 3. It's really a 3 cubed, which means that this is negative 5 over 27, because that's what 3 cubed is. 3 times 3 times 3. And then we have this x cubed, but it's in the denominator, so now we're going to pull up to the numerator and give it a negative power. So when we find our derivative f prime of x, it's going to be that constant just tags along, just like always. Negative 5 over 27. And now we're going to take the power rule derivative here. So we drop the power, subtract 1. Now we're ready to simplify. Well, the negative times the negative, that's going to equal positive. 27 and 3 also simplified. That becomes 1 over 9. So all simplified. This is going to become 5 over 9. And notice that this x to the negative 4 is really x to the 4th in the denominator. All right, we're getting really close here, guys. You're just hang in there. We're doing really well. Okay, so this is that combination play again. We got really 4 over t to the 1/2, which is really the constant 4 times the function t to the negative 1/2. Okay, so taking the derivative of this one, we're going to have s prime of t. That's how we label it. We leave the constant alone. It's just a tag along. And Now we're going to multiply by the power rule effect here. So we drop the power, negative 1/2 t. Now we got to subtract 1 from negative 1/2. That gives us negative 3/2. So then s prime of t, if I were to simplify this, it's going to be 4 times negative 1/2 is negative 2. T to the negative 3/2 means it's going to be in the denominator, but positive. Now I can rewrite that with a radical if I really wanted to. Negative 2 over the square root, the denominator means it's the second root or square root, t cubed. Now just a little note, the index of the root right here, which is that number you write, the default, if nothing is written, is equal to 2. If it says the cubed root of something, that's the same thing as that piece to the 1 over 3, I guess you could say. But it's kind of like writing x to the first power. You know, if we have x to the first power, we just call that x. We have a default. It's 1. But this is a weird one because the default normally is 1 a lot of times, but in this case the default is 2. So just kind of keep that in mind. It's kind of something interesting. All right, last one here. Let's do dy dx. For example, h. Before we even get into that, though, let's simplify this piece. We're going to have a negative 12 over, now I'm going to rewrite this as a fractional power, x to the 5/3. Which if I do that even more, it's going to become negative 12 times x to the negative 5/3. So when I take the derivative, that negative 12 just sticks out front. Now I do power rule for the x to the negative 5/3. So I'm going to drop the negative 5/3 and then raise x to a power that's 1 less. So that's going to be x to the negative now. 3 over 3 would be 1 in this case. So subtract 3 over 3, you get negative 8/3. All right, let's simplify. The negatives put together make a positive. 12 and 3 simplifies to 1 on the bottom, 4 on top. So that's going to give me positive 20, because negative 4 and negative 5 make positive 20 when we multiply. And x to the negative 8/3 means it goes to a denominator. Now we can simplify even more. It's going to be 20 on top, the third root of x to the 8th. Done. Pause it if you need. Remember, I'm moving on. I'm just showing you the example, showing you the work. All right, for this one. Now we're dealing with adding or subtracting. The cool thing is, when you're adding or subtracting, you can treat each individual term all by itself. You don't have to do any special rules. It's almost like you just have separate functions, f and g, and then you take the derivative of each one separately. But only when we're doing adding or subtracting. Multiplying and dividing, that comes in the next video. It's a little more complex. Okay, so let's look at what's happening here. We got x squared plus 5x minus 3. When I take the derivative, just do each term separate. The derivative of x squared is 2x. The derivative of 5x is 5. And this minus 3 is a 0. So that's just 2x plus 5. That was easy. This next one also just as easy, but there's just more to do. The first term, you take the derivative, we're going to drop that power, subtract 1, 4x cubed. This next one, we're going to have minus 3/2 times 3x squared. Then we're going to have plus 2 times 2x to the first. And plus 1, because the derivative of just x is 1. And then this constant, that goes to 0. Okay, so now we can simplify a little bit if we need to. This would be 4x cubed minus 9/2 x squared. And then plus 4x and plus 1. All right. For this next one, what you should consider is that we can rewrite each of these with not denominators but with negative powers. So this first one's going to be 4x to the negative 1. Then we got 4x to the negative 2, and it's subtracting. And then plus 4x to the negative 3. So let's look at the first one. 4 over x to the negative, or 4x to the negative 1. The derivative, which we'll say is dy dx. The constant stays the same. Then we drop the power and subtract 1. For the next one, the constant stays the same. We drop the power and subtract 1. And then for the last one, the constant stays the same. Drop the power and subtract 1. 3x to the negative 4. Sorry, we're losing some space over there. Let's simplify. That gives us negative 4 over x squared, because a negative 2 power means it's in the denominator. Then we have plus 8. Negative 4 times negative 2 is 8 over x cubed. The last one is going to be minus 12 over x to the 4th. So you do a little bit of algebra first, and it makes this a lot easier. Whenever you have that written it with the format x to the n and then a constant out front, that makes it so easy to deal with. All right, this one a little bit more algebra, but still not that bad. We have functions multiplied here, not going to work. We don't know how to deal with that yet, but we do know how to deal with it if it was all added and subtracted, separate individual terms, not grouped. So we're going to ungroup this by distributing. Well, it helps to realize that this x square rooted is really x to the 1/2. And this x third rooted is x to the 1/3. And this x here is to the first power. Why am I being so specific there? Because when I distribute, it's nice to see the powers, so all I have to do is think, how do I combine those two pieces? Well, if you have, keep in mind, x to the a times x to the b is really equal to x to the a plus b. So we're just going to add the two powers. So for the first term, that's going to be 6x to the 1/2 plus 1/3, which is really 5/6. The next one is going to be minus 12, because it's 6 times negative 2. Then x to the 1/2 plus 1 is x to the 3/2. And this last term is plus 36x to the 1/2. So this, we haven't even started taking the derivative yet. We're just prepping it. So for this one, we're going to leave the constant, drop the power, subtract 1. So we leave the constant, drop the power, subtract 1. In this case, negative 1/6. Next one is going to be leave the constant. So we're going to have minus 12, drop the power, 3/2, and then subtract 1, x to the 1/2. Again, leave the constant, drop the power, subtract 1. Now, honestly, we're done there. We don't need to do any more, but if we did want to simplify, then what you would look for is try to simplify fractions here. So we got 6 and 6. That makes a 5, because the 6 over 6 is 1. And x to the 1/6 is really the 6th root of x in a denominator. The negative brings it down. The 1/6 makes the 6th root. 12 and 2 is really a 6 over 1. So the second term is going to be negative 18. X to the 1/2 means square root of x. The last one, 36 and 1/2, is going to make positive 18. But this time it's the negative 1/2, so that means it's in the denominator. Square root in the denominator. Oh, this is y prime, by the way. Y prime. Alright, let's use a different color just so these two pieces don't get mixed up. How about green? Okay, I have a function here being squared. That's an issue because I don't know how to deal with that. That's too complex. It's not individual terms. It's grouped. It's got layers like an onion. So let's peel it apart. That means I should multiply this out into individual terms. I would have 2x minus 3 times 2x minus 3. That would give me 4x squared. I would have minus 6x, and then plus 9. So I have f of x equals 4x squared minus 12x if I combine these two like terms, plus 9. Now all that said, this is pretty easy to take the derivative here. They're individual terms, so we leave the constant 4, drop the power, subtract 1. Next, we leave the constant. What's the derivative of x? It's just 1. And then what's the derivative of just a constant, a horizontal line? That's 0. So simplifying, we'd have 8x minus 12. Excellent, 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 excellent. Let's do this last one in purple, just for fun. Okay, so we're going to do the same thing here because we got a group squared, but notice that the multiplication here is going to be a little more complex. We're doing a square that's 3 by 3 type of area model here. Just to even prep it, we're multiplying this out so we can get individual terms. So we're going to have x squared minus x plus 1. So again, we have x squared minus x plus 1. Okay, so filling this in, we'd have x to the 4th minus x cubed plus x squared. Then the next distribution, if we distribute negative x, we're going to have minus x cubed plus x squared minus x. Then the last distribute, just distribute 1, which means I multiply each of the pieces by 1. X squared minus x plus 1. Okay, so let's look at these like terms. All these x squareds are like, the x cubes are like, and the x to the first power is like. That means I'll have y equals x to the 4th minus 2x cubed plus 3x squared minus 2x plus 1. So then the derivative, dy dx, is going to be 4x cubed minus 6x squared plus 6x to the 1st minus 2 plus 0. Now I kind of did that one a little bit faster, but I hope at this point that you guys are pretty good at doing some of this in your head, because we're dropping that power and multiplying it by the constant. Okay, so that's it. Take a break. And we will see you in part 2.